Take it away, Melissa.
Thank you. Please interrupt me if I'm not clear or if there's background noise and you can't hear. I want to apologize that I can't be there in person, but I want to thank the organizers for making this hybrid so I have the opportunity to talk to everyone today, and also thank Ola and the previous speakers for such a beautiful pedagogical introduction. My talk will be a bit of a change of pace. I'll be highlighting it'll be a whirlwind tour of a bunch of scientific results coming out of both the combination of Gaia and spectroscopic surveys looking at galactic, kinematics, and statistical stellar ages. Okay, so the outline of my talk will be, I want to spend a few minutes just talking about the Milky Way data revolution that we've gone through. Then I'll talk about the populations of the Milky Way galaxy, in particular in the Gaia era, and finally end with statistical stellar ages. First, the Milky Way data revolution. Now, to appreciate the sort of data inventory that we find ourselves in at the moment, I want to step back to 20 years ago, the Geneva-Copenhagen survey, which was this premier survey of about 20,000 F and G dwarfs in the solar neighborhood. And this was this beautiful inventory of ages and proper motions and metallicities and velocities. And this gave us a solar neighborhood understanding of the metallicity distribution, the age metallicity relations, and the age velocity relations in the Milky Way. We can see this, and this is a figure made from that data looking at the age versus the velocity dispersion, showing the total velocity dispersion and the three components of the velocity dispersion in Cartesian coordinates, and there's a gradient. And this is very important for understanding the formation and subsequent evolution of the Milky Way. And this is understood to now be a combination of formation and upside down formation, that is, populations forming kinematically hotter at early times, as well as heating in the disk due to radial migration and molecular clouds and perturbations from mergers in the galactic halo. And they said in this 2004 data release paper that this data was unlikely to be superseded until the Gaia mission and or the RAVE project much, much later. Okay, so let's move to today, where really what I think about the Milky Way data revolution is that we're realizing the Milky Way as a test of galaxy formation, right? The Milky Way is a typical spiral galaxy. We have the majority of the stellar mass in the disk and also in the bulge. And of course, you've seen this Gaia, where it looks like a photograph, and this is measurements of the photometry of individual stars. Now, for the Milky Way, we can uniquely resolve large ensembles of individual stars. And we're in the era of deriving a set, as Ola just presented, of a really large number of measurements from these stars. And we're building up a distribution function of measurements for a large number of stars over a large spatial extent of the galaxy. So we're in a very different era to a decade ago. Right, and this inventory of information that we're getting is things like age, mass, chemical composition. And I'll talk about deriving these things from stellar spectra. And orbits are, of course, coming from satellite missions, measuring stellar motions over time, the premier mission of which is, of course, Gaia. So with all of these data, we're able to realize the Milky Way in both a cosmological context and stars, not as individuals, but as stellar planetary architectures. Okay, this has come about, again, due to Gaia, astrometry, a huge ensemble of hundreds of thousands to millions of ground-based spectroscopic survey spectra, as well as all of these other huge and important missions. Now, what this is giving us, this inventory of information, is across a huge range of temporal and spatial scales. It's essentially a mapping. So this mapping of ages and velocities and metallicities automatically gives you insight and is examining planetary systems and planetary architectures. So where is all of the Milky Way spectra coming from? I just want to pause on this for a moment. This millions of spectra that I'm talking about that's a complement to Gaia is coming from a lot of different surveys. And these surveys are at different wavelengths, different resolutions, and different spatial coverages, and they have different scientific goals. So you may have heard of surveys like Apogee and Galar and Gaia ESO and RAVE and LUMOST and Segway, and of course Gaia has spectra, and there's a whole lot more surveys coming online. So we're continuing to invest in this path of collecting all of these spectra for stars in our galaxy. And just to give you an example of the different spatial coverage, you can see Apogee. This is an infrared survey. The infrared can be sensitive to the very dust dense disk. So this is a survey that observes a lot of stars in the dust extincted disk, compared to Galar, which is a survey off the disk. This is in the optical. It observes stars in the much more solar vicinity and avoids the dust extinction region. So these surveys are all very complementary. Okay, and the deliverables from all of these surveys and all of these spectra are radial velocities, so-called stellar parameters that you've heard a lot about, temperatures, gravities, and metallicities, and individual abundances that all are showed some examples from the RVS spectra of those individual abundances, and I'll talk about those in my talk. I want to highlight Milky Way Mapper, which is a survey that's just come online in the last year or so, because this is very relevant, I think, to this group. It's part of this mapping effort. We're getting 5 million stars across the Milky Way disk with this survey to give us this holistic view of the Milky Way. It's in the infrared, so we can look at the extincted regions of the galaxy right through the disk into the bulge. And the so-called Galactic Genesis survey makes up the majority of this continuous, contiguous map of the disk. But I want to show you where we're going with this survey. So this is looking down on the plane of the galaxy, the XY plane. We're looking down on the disk. The center of the galaxy is at 0, 0. The sun is at -8 kiloparsec in X. The Apogee survey that you may have heard about has been really revolutionary in increasing our understanding of the overall characteristics and the formation and evolution of the Milky Way disk. And you can just see that we're just going to go so much further with Galactic Genesis because we're getting as opposed to almost 1 million stars, 4 million stars, and also hundreds of thousands of stars all the way into the bulge region. We're also moving away from this pencil beam sampling approach of previous generations of surveys like Apogee of getting fields on the sky to getting this full continuous, contiguous coverage. This is going to look a little bit like the Gaia image, except we're getting spectra at resolution of 22,500 for all of these data points. And what we'll be measuring for all of these stars is, again, building this map. Age, we'll be getting an iron abundance and an alpha abundance. And these are really important diagnostics of 2 different channels of element production from supernovae type 1 and supernovae type 2. So that gives us 2 channels of nucleosynthesis. And we'll be getting distances, velocities, and orbits for these stars. So we can understand when they were born, what composition they were born with, and how they're currently moving and where they reside in the galaxy. Also of interest to this particular group is that Milky Way Mapper is many, many programs. And as well as Galactic Genesis, it has a special stellar astrophysics and stellar systems architecture program. And this is to target known multi-star and planetary systems and to target stars with astroseismic detections. It's going to get this volume limited sample of the stars within 100 parsec and target young stars within clusters. So this is really, I think, going to provide a beautiful ensemble of complementary information for planetary studies, both with the full survey and with these targeting programs. Good. So I think I've motivated the data revolution that we have all of these data, getting all of these measurements. This is important for planets. Next, I want to talk about the populations in the Milky Way galaxy, and in particular, what has changed with the ensemble of Gaia and new spectroscopic surveys. The Milky Way architecture in cartoon form looks a little bit like this. We have the galactic bulge, then the exponential galactic disk. We have the sun at 8 kiloparsec away. In the disk, there's these open cluster systems, which are thought to be the building blocks of the disk. These are groups of stars formed from the same molecular cloud that then disperse across the disk over time. There's OB stars in the disk that trace out the spiral arms. These are young stars. And then scattered around the galactic disk, we have the galactic halo, the galactic stellar halo, which has a bunch of substructure that I'll talk about, and coherent systems such as bound groups of globular clusters. So it's been known for some time that different populations, the bulge, the disk, the halo, have different chemical abundances and different orbital properties. And I want to highlight some of these things. First, briefly talking about the halo, which only comprises 1% of the stellar mass, but is a really lovely record of or a capsule of the early formation of the galaxy. Then the disk, the majority of the stellar mass, and shows these lovely signatures, which are a record of the assembly process. And finally, the bulge, which is a really strong signature of formation in the galaxy. Okay, so let's start with the halo. It's been known for a long time, more than 50 years, that there is a relationship between the orbital property of stars and their metallicity. And this is what's shown in this figure. The eccentricity, or deviation from circularity in the plane of the orbit, is shown on the x-axis, and stars that are more eccentric are shown to the right. The UV excess is shown on the y-axis, and this is a proxy for metallicity. Stars with higher UV excess are more metal poor. So it's been known that there is a relationship between the orbital properties of stars and their metallicity. And this has just been really understood in much more detail over the last 50 years. And with Gaia and spectroscopic surveys with regard to the stellar halo, we've now understood that the stellar halo is comprised of a lot of substructure. And the halo has been broadly, in the last few years, recently redefined into a so-called in situ halo, which is heated disk material, and an accreted halo, which is things falling in to the halo over time. One of the biggest early discoveries from Gaia was the so-called Gaia Enceladus or sausage system. And there's different ways of looking at the kinematic reference or the kinematic behavior of these stars. Here, what is being plotted is 3 of the different space velocities, Vy on the x-axis, the square root of the sum of Vx and Vz on the y-axis. And let's turn first to the panel B, which is the merger simulation. This is a disk galaxy simulation where the disk is shown in the black points. It's rotating at about 150 kilometers per second, which is the mean of those black points. And those blue points are a merger coming in at later times. When you go to the data and you just look at the data and plot the stars, you can see that there is also this blob of stars colored in blue that is thought to be basically a replica of what we're seeing in this merger, this infall of debris into the halo of the Milky Way. So there's been this industry in the last couple of years in identifying and understanding halo field structure. It's now thought the Milky Way halo is almost entirely composed of substructure. And this is another, I'm going to show another way of defining the orbital properties of stars and identifying some of this substructure. These figures show the angular momentum energy figure of stars in the Milky Way halo. So these are, if you find stars that are nearby each other in this plane, these are orbitally coherent. Now, these have not, in the right-hand panel, these have been separated into different substructure populations with these ellipsoids. And this has not just been done by identifying coherence in the dynamical plane, but also given their similar chemical abundance distributions. So this is work from the H3 spectroscopic survey, which targets the halo plus Gaia to get the orbital properties. Now, this is, I mentioned this is not only the dynamics by which these are being differentiated and discovered on, but also their abundances. Now, if you work in the field of Milky Way galactic archaeology, which I do, one of the diagnostic planes that you'll see come up again and again for understanding the distribution of stars in the Milky Way is a so-called iron alpha enhancement plane, in this case shown with iron and magnesium, where magnesium is a so-called alpha element. The relevant of this plane is the x-axis represents supernovae 1a production, and the y-axis supernovae type 2 production. So 2 different channels of the origin of elements. And each of these different subpanels shows the full distribution of stars in the Milky Way. Okay, in this plane, stars with metallicities of greater than -1 dex on the x-axis belong to the disk, and I'll come to that in the next slides. And the stars more metal poor than -1 dex belong to the halo and are part of this in situ and ex situ structures. And you can see that 4 of these, I'm showing 4 of these different systems that have been found on the top panel or shown in the top panel. And you can see that these mark out in the different colors, different distributions in these planes. Another really nice result that Gaia, or increased understanding that we're getting from Gaia is of stellar streams. The GD1 stream is really remarkable. This is just shown in the top panel right on sky. You can see this really thin overdensity of stars, and this is our stream structure. If we then take not only a proper motion, but a photometry selection, you can see all these features appear in this stream. And we're trying to understand what is the origin of these features? Why does it have these gaps, these so-called spurs? One of the possible explanations is a dark matter subhalo interaction. Okay, so Gaia is giving us a lot more insight into all of these different structures of the halo and infall and streams that we're seeing, that we're able to see and analyze in much more detail. Moving on to the disk. If we look back to the 80s, it was understood by doing a very simple analysis of looking at the density of stars as a function of height from the plane, that their density distribution traced out what could be described as 2 exponential profiles, shown here in log space. So these are 2 straight lines. And these have 2 different scale heights, a 300 parsec scale height and a 1,350 parsec scale height. And these were described as the thin and the thick components of the disk of the Milky Way. It was later understood that the thin and the thick disk components of the Milky Way corresponded to a so-called low and high alpha sequence in this diagnostic supernovae 1a, supernovae type 2 plane. So these are chemically distinct. Okay, today we've gone beyond samples of thousands of stars that we had in 2004 to hundreds of thousands to millions of stars. And we can see this bimodality here shown from the Apogee survey in much more detail with all of the halo stars with metallicities of less than -1 dex. With this mapping of the supernovae plane and spectroscopic surveys, as well as Gaia, we can look at the empirical landscape of the Milky Way disk all the way into the bulge. And that's what I'm showing here. I've got lots of subpanels now of this supernovae plane. This is iron alpha again, looking at from the inner region of the galaxy. This is all the way into 2 kiloparsec. The center is 8 kiloparsec, all the way out to 17 kiloparsec. So let's focus on just the solar neighborhood. Okay, just directly around us, we can see this bimodality that we've known about for a very long time. And you can see there's this transition as you move from the inner to the outer region. In the inner region, the high alpha sequence dominates. It's thicker spatially. It maintains the same sort of shape as you move out in radius. But if you now look at the low alpha sequence, the gradient in this plane flattens as you move out further and further away, and the high alpha sequence disappears. So by the time you're out in the outer disk, you're only seeing the low alpha sequence, which is concentrated to the outer region and thinner spatially. So there's a lot of debate as to what has set this chemical distribution of stars. It almost looks as though there's 2 galaxies on top of one another chemically. If we look now, if it's very useful to break up the high and the low alpha sequence and examine their properties separately in the Milky Way galaxy. And this is what I'm showing here in the XY plane. Again, looking down on the disk, the sun is again at -8 kiloparsec on the x-axis. The center of the galaxy is at 0, 0. And what is being shown at left and right is this low alpha sequence and this high alpha sequence respectively. So what you see is there's this beautiful gradient in metallicity in the low alpha sequence from metal-rich stars in the center of the galaxy to metal poor on the outskirts. If you look at the high alpha sequence, it's completely homogeneous. So these 2 populations look to have had very separate formation and evolutionary histories. As well as that, we've known from small samples and more recently from much larger samples that the high alpha sequence is primarily old, the low alpha sequence is primarily young. Okay, good. Another really interesting characteristic of the disk is that in the disk, stars are born in, or thought to be born in open clusters, and they move over time. So these stars that are born in clusters, they have presumably identical abundances. And this is represented by this simulation showing a molecular cloud with these different groups of stars forming. These different colors are supposed to represent that these are unique chemical fingerprints. We might be able to measure 30 elements for these sort of stars. And within each of these little separate colors, those elements would be identical and different to the other clusters forming around it. These then disperse over time. Okay, clusters dissolve, and then due to processes like radial migration, where the bar kicks stars out and the spiral arms move stars in and out, these stars basically end up a long way away from their birth sites. Now, one prospect to trace back the disk assembly that has been proposed is chemical tagging. And this is identifying individual stars across the disk from their birth sites using their large vector of chemical abundances. So using a star's chemical abundances to be able to bin stars back into their individual progenitor open cluster systems. It turns out chemical tagging is very difficult, but we can use the joint information that we're assembling from all of these surveys to make some good progress in understanding the disk formation. The reason that it's difficult is that stellar abundances are very correlated. Okay, spectra is very low dimensional, it turns out, in the disk. That is, we don't have the discriminating power in abundances to put all of these stars back into their individual progenitor systems. But we can do powerful population analyses looking at the distribution of orbits, really important that Gaia is giving us these orbits, as well as metallicities and individual abundances that we measure from spectra of ground-based surveys. Okay, I just want to show one example of this sort of analysis whereby we're seeing cluster dissolution in progress. So how are we seeing cluster dissolution in real time? Well, what this plot is showing, this is the Milky Way data on the left and a smooth Milky Way disk model on the right. This is pairs of stars. And what is being plotted is the orbital similarity of pairs of stars on the x-axis, where things on the left have closer orbits. These pairs have closer orbits. And on the y-axis, this is the fraction of stars with similar or very identical within the errors metallicity. So as you move further up, as you move further up on this figure, you're getting to more pairs with identical metallicities. So you see in the smooth Milky Way model, it's flat on the y-axis as you go to closer orbits, but in the Milky Way, you get more and more pairs of stars with identical metallicities as you go to closer orbits. And this is thought to be due to the clumpiness, the dissolving clusters that we're actually observing using the distribution of many, many stars across the disk, okay, in this sort of functional form. And this is a really nice example of using a statistical analysis to do that. We also know that the disk is out of equilibrium. And with Gaia, we can just see the perturbations from the bar, the spiral arms, and the satellites in the velocities and the metallicities of stars. This is a really nice example of seeing a perturbation. This is the so-called, it's from a paper by Antoja in 2018, the Antoja spiral. This is looking at, for many, many stars in the solar neighborhood, the Z versus VZ. So that is their height from the plane versus their up and down motion in the plane, colored by their rotational velocity. And you can see this traces out this spiral. And what this spiral turns out to be, this overdensity in VZ and also seen in density space, is a signature of phase mixing of stars with different frequencies of their orbits. So this is thought to be a signature of a perturbation, such as from the Sagittarius dwarf tidal interaction. We see the Sagittarius dwarf in our galaxy, and this is thought to be the kind of perturbation that you would get from that satellite infall. Okay, and with Gaia DR3, it's been possible to do a much bigger analysis of this spiral structure. And this figure now shows this spiral mapped over different spatial extents from the inner galaxy at left to the outer galaxy at right, moving in azimuth around the disk. And if you look in detail, this spiral changes as you move around the galaxy. So what actually happens in the inner region is you end up not with one spiral, but two different spirals. And this is thought to be due to multiple perturbers, things like infall, but also the bar in the inner region that I'll show in the next slide. Good. I want to end in our populations with the Milky Way bulge, because simulations predict that a bulge formed from the disk will be boxy or X-shaped. We see this in all sorts of simulations. I'm going to show you three different simulations, different types of simulations. The face-on view, that's the XY plane I've been showing, as well as the edge-on view and the side-on view. And the edge-on view at the top really shows this X-shaped structure. Okay, simulations show that if you start off with just an exponential disk, that after a brief amount of time that experiences some instabilities, and the orbits or the stars go into orbit families that trace out an X-shaped structure in the inner region. We see this in N-body simulations, dissipational collapse simulations, and cosmological simulations. And this is a consequence again of orbit families from dynamical instabilities. This is a very ubiquitous thing that is seen in these sort of simulations. Now we also see this X-shape just directly in the photometry of the Milky Way in the infrared. So this is seen in the unwise photometry from the WISE satellite. You can just see that the inner region of the Milky Way traces out these X-shaped arms. It looks, if you're very observant and you have good eyes, you can see that it is larger on the left-hand side, and that's because it's a projection effect. The bulge is on an angle with respect to us of about 27 degrees. Okay, so this is a strong signature of a bulge that is formed from the disk by dynamical instabilities. And these things are common. Lots of galaxies show this sort of structure. I just plucked these 6 galaxies from the very first JWST image. I zoomed in on a couple of these structures. What X-shaped bulges are parts of bars seen side on. There's lots of barred galaxies. They have lots of variability in their shapes, their sizes, whether or not they really reveal the X-shape or not. But overall, the formation processes are thought to be the same. And you can see this particular one at the bottom, which is a side-on galaxy, almost also looks to be very X-shaped, like our own Milky Way. Another, I think, interesting point to bring up in the context of this workshop is with these large spectroscopic surveys, we're observing many rare stars. And lithium-rich stars are, I think, particularly interested from a planetary perspective because lithium is destroyed and depleted at all stages of evolution. Yet we see stars that are enhanced in lithium. So this requires a production mechanism. One of those proposed production mechanisms is planet engulfment. Now, you don't expect to see planet engulfment equally everywhere. The most likely place to observe enrichment from planetary engulfment due to the lifetime of where stars live and also how long the enrichment signature lasts will be on the subgiant branches. And this is shown in this simulation, looking at temperature versus luminosity of stars, looking at these stellar isochrones, that you're most likely to see planetary enrichment on the subgiant branch at around 1.4 to 1.6 solar masses. Now, in the observational world, we've identified the largest catalogue of lithium-rich giants, not lithium-rich giants, lithium-rich stars all over the temperature gravity plane. So we have 8,000 of these stars enhanced in lithium. The color bar is excess equivalent width. It's not a direct lithium abundance because this has been measured directly from spectra. But you can see that we have a whole lot of these candidates in the subgiant region that may have had their lithium enhanced due to planetary engulfment. So I think there's a lot of connections to be made between the theoretical and the observational realms here. Good, so I want to end. I've talked about my Milky Way data revolution, the populations in the Milky Way galaxy, all of this beautiful science results that we're getting from Gaia, and I want to end by talking about statistical stellar ages. Now, how are ages typically measured? And we heard about this a little bit earlier today. We'll also see a talk by Marina after me. And Dan, I'm going to actually talk about a couple of the ways that Dan did yesterday in far less detail, but focus more on some of the scientific results. So how have ages typically been measured? Well, a typical way of getting ages has been for the subgiant branch. If you have a temperature and a luminosity, there is discriminating power in stellar models here that you can see reading directly off this plane. These are models with different ages. So if you know the luminosity and temperature precisely enough, you have a precise age for your star. And this is really been good for small nearby samples. And this is where Gaia is going to provide the most precise ages. You heard from Ola, and I'm talking about for field stars, not stars where you have additional information like stars in binary systems. And we heard from Ola that Gaia is providing ages across all of the temperature luminosity plane, but this is really, I think, where they're going to be most precise. And we can look back a decade and look at this diagnostic alpha metallicity plane, and we can see this result that I showed earlier, that low alpha stars are young, high alpha stars are old. Okay, but alpha's been a proxy for age, but it's not age itself. If you look at any slice in the alpha enhancement of a star, this alpha element from supernovae type 2, you can see that there's a range of ages. A more recent way that ages have been measured for relatively small samples of stars, and this is something that Dan talked about yesterday, is astroseismology, right? This is very long cadence or long baseline, high cadence observations of stars from which we can construct their power spectrum and tap into their internal oscillation frequencies and determine a stellar mass from those oscillation frequencies. And if you have a red giant mass, as shown on the x-axis, and you know the metallicity, you can use stellar models to go to stellar age, which is what's being shown in this figure. Okay, so I want to focus now on just a couple of science results, looking at small samples of subgiant stars and also ages from astroseismology. And both of these are considered precision regions of age dating in the sense of getting ages precise to 10 to 15%. So firstly, looking at main sequence turnoff ages, where Gaia is going to provide high precision ages for stars within 2 kiloparsec. These are faint nearby stars. There's been this beautiful result that looks at the age versus metallicity distribution of stars. And you can see there's this really fascinating chevron structure that is traced out in the solar neighborhood, in that the stars become at the very more metal rich end older and the more metal poor end older, with this so-called turning point in the middle. Now, this turning point is a signature of formation. This is thought to be a combination of, again, the Sagittarius mass infall with the Milky Way, and also stars moving from their birthplaces over time and mixing across the disk. Okay, we've also been able to age date different halo populations using the main sequence turnoff, and this is showing some results from the Gaia and H3 survey. The different histograms represent different populations. The oldest is the accreted halo, followed by the in situ halo. Underneath the in situ halo is the high alpha disk, which is thought to be it's associated with this population, and the low alpha disk is sitting at the smallest age, or the lowest mean age distribution. So we're able to get overall precision age distributions for different populations in the Milky Way. Now, with astroseismic ages, this gives us precision age distributions, for example, of the alpha sequences. And this shows that for the high and low alpha sequences, which are traditionally thought of young and old, that actually in the high alpha sequence, it's been confirmed that there's this interesting population of young high alpha stars. And in the low alpha sequence, there's this interesting population of old high alpha stars, which has strong implications for either chemical enrichment or physical properties happening in stellar binaries. We're also using these astroseismic ages, can also age date halo structure using small samples of stars. and start to combine ages with abundances to look at age abundance relation for the elements measured in surveys like apogee. This is what I'm showing on this figure with age on the x-axis, individual elements on the y-axis. They're labeled at the top: iron, carbon, nitrogen, oxygen, and so forth. And the thick line just shows the mean of these relations, and the line around that is the 1 sigma standard deviation. So these are 100 red giants with ages from astroseismology at solar metallicity. And it turns out the intrinsic dispersion, the scatter around these relations, is very small. It's on the order of 0.02 dex or 5%. What's happened in the recent years is these relations have been inverted, so that rather than just looking at the correlations, individual abundances can be used to infer age, given that the correlations with age are so tight. And there's a number of different research works that have done that. What's changed in the last few years is we can now measure ages for giants spectroscopically. So this has meant a regime change, moving from stars in the solar neighborhood to being able to age date stars all across the galactic disk of the Milky Way for the footprints of these large spectroscopic surveys. So this shows the apogee footprint, and we're going to be able to label most of these stars with ages by deriving ages from their stellar spectra. How do we do this? We need a reference set of stars with known mass. We have about 6,000, and we had at the time red giant stars in apogee that are also observed by Kepler. So their mass is available from astroseismology. And we use these to create a data-driven model. And I'm going to step you through a few slides explaining how this works, because I think it's easy to explain and it's fun, but there's many data-driven models available. The Canon is just one example. So with data-driven modeling, you build a model using some subset of data, and you apply that model to the rest of the data. And this has been used in recent years to label bad data, using models built from good data, to extract so-called new information from data where new in this context, it was always there, but hasn't been extracted previously. And also what I won't talk about in much detail is you can use these models to see where the information resides in spectra, which I think is really important. One of the questions that came up, we can correct stellar models in this way, physical stellar models. This is an incomplete list of some of the work in the last couple of years that has used data-driven modeling approaches. So how the Canon works on spectra, and indeed any other data-driven label transfer, is it relies on a subset of n reference stars in a survey where you know their labels. And then it uses those reference objects with their known labels to build a model. And this is the training step. This looks like this. The flux of your n reference objects at every wavelength is equal to some function of your labels, where I'm going to show the example of temperature, gravity, metallicity labels, although then we'll add in age. It's the exact same process, given your spectral model, which again, I'll show an example of, plus your noise, where your noise is two things: your photon noise, plus the fit of your spectral model, which is going to parameterize how good the model is. And we're going to do this at every wavelength. And this essentially just relates stellar labels to stellar flux at every wavelength. That model is then used to infer the stellar labels for the remaining stars in the survey at test time. I'm going to show this on the apogee example to infer 3 labels in the infrared. The training set is going to be only 540 open and globular cluster stars, where we have a good handle on the stellar parameters. They have a broad range of metallicity, 3 labels. This is what our model looks like. The flux of our n reference objects is equal to some coefficients that we're going to solve for at every wavelength, multiplied by the linear, cross, and squared terms of the labels that we know, because they're our training set. We know everything about them, their flux and their labels. Their labels are coming from a physics-based pipeline, ASCAP. The test set is 120,000 stars from apogee, and we're going to use the exact same equation. This time we know our coefficients. We've just solved for them at training time, and at test time we're going to now solve for our labels of temperature, gravity, and metallicity. So how well does this work? Well, 2 tests to show this. First is the take one out test. This is where we're going to look at temperature, gravity, metallicity from top to bottom. We're going to take one star out of our training set, train our model, and infer the temperature, gravity, and metallicity for that star, and plot all of those inferences together. And so we see that straight line is the 1-to-1 line, and that shows the precision to which we can infer these different labels. Okay, I'm not going to go into detail about what that precision is, but you can see basically it's following the 1-to-1 line. It's working very well. Another way we can look at this is to examine a generated model versus our star, our real data for our test objects. And this is what I'm showing here in a data versus model for 4 narrow regions of spectra. You can see that the data and model are a remarkably good match. Okay, they're not perfect, and this improves once you add additional labels describing the variability of the spectra, namely age. Okay, I have 2 more minutes. I can see I'm at time, but I have 2 more minutes and then I'll be done. So to learn our age, we need a reference set of stars with known mass. Again, we have these stars. These are stars in apogee, also observed by Kepler. Now our labels are going to better describe the spectra rather than temperature, gravity, and metallicity. We're going to have temperature, gravity, metallicity, alpha enhancement to get 2 channels of enrichment plus our mass. The first set of these come from apogee spectra with the ASCAP pipeline. The mass comes from astroseismology, from the so-called seismic scaling relations. The nu max and delta nu terms that you see in this equation are derived from the power spectrum. This model is then used to determine the masses for the rest of the apogee giants, and we can go from the mass to the age with stellar evolution models. The origin of the mass information, this only works because the mass information is there. It turns out in the apogee spectral region, and this shows 1% of the apogee region, that the mass information is in carbon and nitrogen features. And what's being plotted is 2 different spectra, one with solar mass of 0.7, one with a mass of 3.3 solar masses. And you can see these very, very, very small changes that are carbon and nitrogen features. And this is physically motivated because mass-dependent dredge up alters the surface carbon and nitrogen abundances. These are very subtle signatures, so we're only able to infer the age of stars to a precision of about 30%. So we're not able to do anywhere near as well as these other methods in terms of precision, but we're able to do this for many, many, many more stars over a larger spatial extent. And models such as the Canon can leverage this indirectly, or the carbon and nitrogen can be leveraged directly with age calibrations using either astroseismic stars or clusters. Now, what this has given us is the ability to make big age maps over the entire extent of the disk. Here I'm showing galactocentric radius on the x-axis, height from the plane on the y-axis. What we previously had was mostly ages around the solar neighborhood, shown in this little circle. Now we have ages over the entire disk. We can see old stars versus young stars. We are able to see this evidence for inside-out formation because of the old stars in the center, the young stars in the outer region, and this flaring of the disk, right? You can see that the disk is flaring as you move out in galactic radius. Over the next half decade, we're going to get ages for, or fill in basically all of this bulge region with ages for millions of stars from Milky Way Mapper, and we can propagate ages between surveys given stars in common. So putting everything together, ages are key. There's different, I'm not going to go into this work, I just wanted to put these up as a reference. These slides will be available. There's work that looks at reconstructing, winding back the Milky Way over time with these ages, at mapping, basically what is the empirical distribution given all of these different, the relationship between orbits, ages and abundances, and also signatures of formation, looking at the age metallicity relation, age dating, that phase space spiral that I showed, looking at the bulge versus the disk. I'm going to skip over my last slide in the interest of time and just conclude with saying we're really at the point of next frontiers where we have this ages, kinematics, and abundances mapping, and that's getting us to architectures. There's galactic scale architectures and planetary systems architectures. And I think we owe a big debt of gratitude to Gaia and these ground-based spectroscopic surveys providing us with this public data. And it's a very exciting time with all of this ensemble of data and surveys pushing fields together. So I think this provides us with a lot of opportunities. So please reach out to me on Slack if you have any questions, and thank you very much for your attention.
I think we have time for a few questions. What was that?
Yeah.
So, if you are want to come out to the other side while we're doing that, do you have any questions from the Slack?
So we have the first question is, you showed plots of metallicity versus alpha showing the thin and thick disk sequences. The first question, are all the alpha-rich stars, even the iron-rich ones, old, or have young alpha-rich stars been found?
Yeah, it's a really young, this is, I think, the best figure that shows this, that shows from the astroseismic that I have in my talk, the astroseismic results showing that young, it shows the high and the low alpha sequence, showing that for the high alpha sequence, there are young alpha rich stars. And there's a lot of debate about whether these are real and a consequence of chemical evolution, or whether they're due to just mass transfer from binaries, and they're just masquerading as young stars. But this is a very active, a lot of discussion going on in the literature looking at these stars.
The second part of this question is that why are the alpha rich and alpha poor sequences so well separated?
So well separated. Yeah, so there's different reasons thought to be did that. There's natural explanations in terms of chemical evolution, that there is a natural transition. There's also thought to be that they formed from completely separate events, that the high alpha disk formed first and the low alpha disk came in a gas-rich merger. So there's both observational work that seeks to explain this and simulation work, and I think we don't have a clear consensus on that yet.
One from Pasadena. Can you hear me?
Yep.
What are current prospects for finding stars in the sun's birth cluster through strong chemical tagging?
I would say that I'm pessimistic for those prospects because of the low distinguishing power in the chemical abundance distribution, in that abundances are very correlated. And if you take a random pair of stars, 1 in 100 are chemically as similar as stars in open clusters. We've done these sort of tests. I think the Galar survey has the most chemical distinguishing power. That measures 30 different element abundances in the optical. And I think that will give us the highest resolving power. But the work we've done so far indicates that the resolving power of abundances is not as high as required for this sort of pursuit.
Thanks.
All right, I think we have time for one or two more questions online.
Okay, so another question from online. Do you have any thoughts on how the spectra, RVS and or BPRP from Gaia DR3 are more or less useful than some of the accompanying spectroscopic surveys you mentioned, like Gala or Gaia ESO?
Sure. So starting with the BPRP, that's fantastic for stellar parameters and I think overall metallicity, not for individual abundances. For Gaia RVS, we've done some tests on that and showed that the majority of information in the spectra is described by temperature, gravity, metallicity, alpha enhancement. Whereas when you go to Gaia ESO or the Galar survey, you're tapping into additional channels of nucleosynthesis, primarily the neutron capture family, which isn't very well, which isn't able to be measured, I don't think, from the Gaia RVS spectra. I think it's also relevant to note from the Gaia RVS spectra, there's a dib in that spectral region, which I think is going to beautifully be able to map the interstellar medium through the pooling of stars. But the surveys are very complementary in that the higher resolution optical surveys in particular are getting this multiple channels of neutron capture from neutron star mergers or collapsars and AGB stars.
All right, let's take one more question in person and then we'll break.
Hi, Malaysia. Through Gaia data release 2, we were able to study the galactic bar and we had more details about it. And in the recent study, we were able to know that the galactic bar is slowing down.
Mm-hmm.
So in how many ways and in what ways do Gaia's data release 3 shed more light on that? And what will be the principles or reasons behind the slowing down of the galactic bar? And does that shed any light on the dark matter?
Definitely, I think yes to all of your questions. My understanding is the bar slows down or is thought to slow down, and that's seen in simulations due to angular momentum exchange with the dark matter halo. And that really changes the perturbations that you see imputed in the galactic disk. And I think the relevant point about Gaia in the spectroscopic surveys is because we have the spatial mapping, it should impute, I think, azimuthal signatures, which should be able to differentiate from a constant bar and a slowing bar. But I think that's a big open question for the future.
Thanks.
Great, let's thank Melissa one more time.